That's correct.
Does it look like everybody does, I guess? Science is not sure.
Anyone else?
Okay, well, let's just go ahead and start. I'm Professor Clay, and I'm going to talk to you today about the field that I work in. It's called geometric group theory. And so the idea behind geometric group theory, so I mean, we study groups, which are algebraic objects, but we study them using the topology and the geometry of the spaces they have. So that's sort of the mantra behind geometric group theory. If you want to study groups, these algebraic objects, by looking at the topology and geometry of the spaces they have. Okay, so we'll go through this kind of slowly. I'll kind of remind you, what a group action is. We'll look at some examples. And then we'll look at some examples of how the topology and the geometry can actually tell you something about the group. Okay. So first off, let me just sort of remind you what a group action is. And so what is it? Well, there's really sort of three things here, right? So if I have some group G acting on some set, which I'll call capital X, and maybe X is just a set, but maybe X has some structure to it. Right, so maybe X, I'm thinking of X as like a complex point. And so then I should be acting by like homomorphic maps. Maybe X is a group itself, in which case I should be acting by automorphisms, or maybe X is some sort of metric space, in which case I should be acting by isometries. But the idea here is that for each element in the group, right, there is some function, which I'll denote f sub g, which goes from X to X. Right? So some sort of bijection. Follow some of the other things, right? So there's some bijection of the set which preserves the structure, right? So like I said, I mean, if X is a group, it should preserve the algebraic structure. If X is a complex plane, maybe it should be a holomorphic map, right? Something preserving the complex structure. So this assignment of maps for group elements, right, should agree with the structure in the group, right? So composition of these functions should agree with the multiplication from the group. So I look at the function corresponding to GH. It should just be the composition of the functions of G composed with the function for H. So for all elements in the group. And then lastly, the identity element in the group should act as the identity function on the set. So this is what we mean by a group action, right? So every element in the group gives me some sort of bijection of the set to itself, preserving some structure. And composition of function agrees with the group multiplication. Okay. Okay. So what are some examples? Okay. So first example is you can think about the group of integers. Okay. All right. So just integers z acting on the real numbers. And by the action, so I just need to describe for you what a function I assign to each integer. And the action here is going to be by translation. So what does that mean, right? So, given some number n, an integer n, right? Fn, this should just be a function from R to itself, right? Some bijection. So this is some function from R to R. Right, and the definition here is that Fn of x is x plus n. And so you just slide the real numbers, n units to the right. Or to the left, right? This is indeed an action, right? So let's see. First off, I've satisfied the first rule, right? Every integer is assigned some sort of function. This is a bijection. A bijection from R to R, just subtract off n to get the inverse. So let's just see that it satisfies this this rule here, right? Forgive me, but when I'm talking about the integers, right, I'll write down the multiplication as addition. We typically normally do, right? So we can just sort of check, right, that Fn of Fm of x Right, if I just write down what is this composition, right? Well, it's Fn of x plus m, which is of course x plus m plus n. Right, and of course the associative law tells us that that's the same thing as x plus m plus n. Probably didn't notice that I was saying different things there. Which is the function assigned to m plus n. Okay, so it does satisfy that second rule there, right? That the composition of functions agrees with the group structure. Okay? And then of course, right, the f for the zero element, right? In this case, it's the Abelian group, right? So we can talk about the zero element. The identity is just the identity. So this is a good example here of a group action. Good, happy? I like that one. So let's look at another example here of a group action. So let's look at the group which is called SL2R. So the SL stands for special linear. So this is a group of matrices. The 2 means that they're 2 by 2 matrices, and the R means that all of the entries are real numbers. Right, so these are 2 by 2 matrices where A, B, and C, D are all real numbers. And the special condition is just that the determinant, right, which is AB minus BC, should equal 1. This is what's called a special linear group. 2 by 2 matrices with coefficients in R. The SL just means special linear. Okay, this is indeed a group of matrices. And what does this act on? Well, this acts on a number of things. One of the things this acts on the upper half plane. So let me write this with kind of a fancy H. So these are a set of complex numbers where the imaginary part is positive. All right, so what's the action here? I mean, really, acts on a number of things. I mean, the complex plane, the whole thing, but it also acts on this subset. It's kind of a classical action that people study. What's the action? Well, so for each matrix, I just need to describe for you some function of the upper half plane to itself. This is what's called a fractional linear transformation. So given a matrix A, we'll just call it, say, A, which is the matrix from A, B, C, D, right, and the group SL2R. I'll just define this function, f sub A, which just takes a complex number and does the fractional linear transformation, AB, AZ plus B over CZ plus D. Okay. So what's called a fractional linear transformation. Class in complex analysis. C means, hopefully. All right, and it's a fun exercise, I guess, to check that composition of these functions really agrees with matrix multiplication. So if you've never done this exercise or seen it done, when you're bored tonight, something else to watch on TV or something, I mean, you can just check, right? Take another matrix, give them A1s or primes or something like this, and you can just write down that when you do the composition of these functions, it really does the same thing as just matrix. And then you can also check that if something has positive imaginary part, that when you do the composition, you still have positive imaginary part. And this is where this property here, that this determinant is positive, in fact equal to 1, will come later. Okay? Is that good for group actions? Okay, lots of fun. Okay, so well, the whole idea of geometric group theory, right, is to study groups by looking at the topology and the geometry of spaces they act on. Then, given some sort of random generic group or something like this, hopefully it acts on a number of spaces, right? Or hopefully it acts on some space, so that I can try to say something about some sort of geometry, telling me something about the group. Okay, so there's a sort of a canonical object that we can associate to a group that really gives us kind of a geometry to work with. We have sort of one space that we can at least look at when trying to understand it. This is what's called the Cayley graph. So let me go ahead and describe for you this construction of what's called the Cayley graph given a group, and then we'll look at some examples. Okay, so I need to start with some group, G. I'm going to start with some subset S, which is called a generating set. For my group G. Okay, so you should think of this much like you think of a spanning set from linear algebra. It just means everything in the group can be written down as a product of elements in this. Okay. So every G can be written as, S1 plus or minus, S2 plus minus, blah, 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 Sn plus minus 1, right? So where these SIs belong to that set, capital S. Okay, it's like a spanning set for a vector space. It's not saying anything about uniqueness, right? It's not like a basis by any means. I'm just saying that I can write down everything as a product of these elements in some order, possibly repeating them anytime. Okay? All right, so given a generating set for a group G, we define this Cayley graph. Okay? And the way that we do this, well, I just need to tell you what the vertices and the edges are. And this will build for me some graph. And then what we'll see is that this group here will act on the graph, and one of the things about geometric group theory is it's really trying to understand how the geometry of this graph can influence the structure of the group. Well, this is some sort of abstract graph, right? So I don't really have too much choices here for what I should put the vertices. The vertices are just the group elements. So I have one vertex for every group element. Okay, so that's the vertex set. Now I just need to tell you when to connect up to by an edge. And we connect them up by an edge whenever they differ by one of these elements in our generator. So I'll have an edge between an element G and an element H when I can write H as G times S, where S is in my generator. That's a lowercase s and that's a capital S. And sometimes we'll draw a little arrow here and we'll label that edge as. Okay. So we'll look at some examples here, but this is this abstract graph where the vertices just correspond to group elements, and I put an edge there whenever they differ by a group element. And I say differ by a group element, right? Because if H equals GS, right, then you can multiply this at, you can multiply H on the left by G inverse, right? This is really the same thing as saying that G inverse H equals S, right? So that's kind of like, the multiplication way of writing. Right, so if their difference is one of these generators, then we put an edge between them. It's kind of easier to think about it. Okay. So this is some graph. Let's give some notation to this thing. Let's call this gamma G. This is the Cayley. Okay, so let's go ahead and look at some examples. Examples are fun. So the first example that's kind of easy to understand is if I look at the Cayley graph of the integers using the generating set consisting of the number 1. Right, 1 is a generating set for the integers. Right, every integer can just be written as 1 plus 1 plus 1 plus 1 plus 1 so many times, right? Or minus 1, minus 1, minus 1, minus 1. So 1 is a generating set for the integers. So what does the Cayley graph look like? Well, the rule says I should draw one vertex for every element in the group. So let me go ahead and do that. Of course, I'm not going to do every element in the group because it would be here too long. Yeah. Okay, and then I'm supposed to draw an edge from one element to the next when they differ by one of these elements in the generator, right, which is the number 1. Okay. And so the edges that I'm going to get are sort of the obvious edges that are staring you right in the face. Right, there's an edge from 0 to 1, right, because, well, 0 plus 1 equals 1, right? And that's my condition, right? 1 plus 1 is 2, right? So I get that edge there. 2 plus 2 is 3, and so forth. And that's a picture of a Cayley graph then for the integers using the generating symbol. Right? Really, it's sort of a combinatorial model of the real one. Okay, is that good? Okay, so let's look at another example here. So let's look at the Cayley graph of the group. So let's look at a finite group here. Let's take the group of integers mod 4, direct sum, the integers mod 2. So in other words, I have this abelian group, which is generated by an element of order 4 and an element of order 2, and those two elements are independent. Okay, so as a generating set, I can just take an element of order 4, let me write that as 1, 0. An element of order 2, I can write that as 0, 1. Right, and, I mean, just like you have, your sort of your standard basis for, thinking of R2, this, is going to give you a generating set for this group, right? To sort of do the obvious addition. So let me go ahead and give these guys some names though, so I'm not writing ordered pairs. Let me go ahead and call this guy A, and let me call this one B. Okay, so let's go ahead and try to draw the Cayley graph for this group using this generator. Okay, so there's 8 elements, right? I have a product of a group of size 4 with size 2, so this will give me 8 elements. Let's go ahead and try to draw the Cayley graph here. So starting with the identity element, right, which is an abelian group, so I'll write that as 0. Right, if I just start adding on this generator A, I'll get A squared, A cubed, A to the 4th, which brings me back to 0. So I see I have this cycle of length 4 sitting here inside of the Cayley graph. Right? If I add on A, and I'll do A in blue and B in red to kind of keep track of the edges. So this will give me A squared, A cubed, and back down to the identity element. And that's really half of the elements here in the group. The other half come from taking these 4 and then adding on the element. And that's my other generator. And so you see sort of from sticking out from these ones here, we'll have edges labeled B, which I'll just draw in red. And so this will be the vertex corresponding to B. This will be the vertex corresponding to AB, A squared B, A cubed B. Okay. Right, going from the identity to B, right, is using this generator here, going from A to this one, right, I'm just multiplying on the right by that generator B, and so I have that edge there corresponding to B, which I'm going to draw. And I'm not going to put an arrow on this one, right? Because really there should be an edge going this way and an edge going that way, right? Because B times B, since B has order 2, right? It's in the group Z mod 2. Since B is order 2, there really should be a red edge going this way and a red edge going that way. But to kind of make the picture a little clearer, oftentimes what people do is when they have those loops, they just kind of smush them together and don't put an edge. Just to kind of make the picture look a little clearer. Okay, we're not quite done though, right? If I need to think about what's going on here, right? If I multiply, or if I add, say, A to this on the right, that'll take me over to BA, which is the same thing as AB, because this is an abelian group. So I'll also have edges that kind of go around this way as well, corresponding to, adding or multiplying, well, think about this, the generator A to the corresponding group. And so that's a picture of the Cayley graph for this group Z mod 4 plus Z mod 2 with respect to this generator. Right, so there's 8 vertices corresponding to the 8 group elements, and we connect them up, right, whenever they differ by an A or a B. And because this is an abelian group, right, we don't really care about the difference between left and right. Whereas, the definition over here, did write that thing on the right. We'll look at some, non-abelian groups here. Okay. Good questions?
Is there any way to estimate or calculate how many edges you expect to show up for a group?
Yeah, that's a good question. So yeah, I mean, if it's an infinite group, of course that question doesn't really make sense. It's infinity, right? But if it's a finite group, so every vertex really should look exactly the same, right? You see this in this picture here, right? Every vertex in this picture has degree 3, right? Because I've kind of smushed those 2 edges together. And so since every vertex has the same degree, you can compute the number of edges in terms of the number of vertices. Right, this is what's sometimes called the handshaking lemma. Just some bonus math for you. Now, whenever you have a finite graph, if you take the sum over all of the vertices, that's a little d and a capital D, and you sum over their degrees, you always get 2 times the number of edges. Right? So the number of vertices would just be the number of elements in the group. This degree, well, really it should be 2 times the number of elements in the generating set that you have there, right? You have both one for an A and this other one, kind of an incoming A and an outgoing A is kind of what you have in each of these. And this equals 2 times the number of edges. So why is this called a handshaking lemma? That's a good question. It has anything to do with handshakes. Well, if you have a bunch of people in a room, you can think of those as the vertices. They walk around and introduce each other. They shake hands. And you say, well, how many handshaking experiences happen or something like this? Okay, or how many, handshaking events, there we go, that's a better one. Well, you can model this by a graph, right? Where the people are the vertices and you connect 2 of them up by an edge if they shook hands, okay? And so then the number of edges is the number of handshaking events that occurred. And how can you count that? Well, you just count the number of hands that everybody shook, but that counts every handshake twice, right? Because there's 2 people in a handshake. So there you go, there's a handshake. Okay. Okay, good. All right. Yeah, so let's see. So this is a graph. Like I said, we really want to be thinking about things with a geometry. And so you can turn this into a metric space by just declaring that every edge has length 1. So you can make this becomes a metric space. To say that every edge has length 1. Or you can fix your favorite number, but as it turns out, it doesn't really matter. So might as well go. So in other words, with this combinatorial picture here of the real line, really now it just is the real line, right? There's one unit of distance, right, between the consecutive integers, and you can even talk about this point in the middle, right, as really corresponding to being 1/2 of the vertices. Or the same thing here, right? If you wanted to measure the distance between these 2 vertices, well, you just look at find the shortest path, and so the distance between those 2 vertices would be 3. Okay, so we can turn this thing into a metric space. Right. And in fact, now we also have that the group G acts on this space. So we really get an action of this group on this metric space. So how does it act? Well, it acts on the vertices just by left multiplication. So if I see some edge in my Cayley graph, label these things. Let's see, I'll label this H, HS. All right, so if I have some edge in my Cayley graph between some vertices H and HS, well, what should the group element G do to this? Well, I'm just going to multiply each of those vertices on the left by G. So the vertex H will go to the vertex GH, the vertex HS will go to the vertex GHS. And this is why I need to do things on the left and the right. right? Because multiplying on the left doesn't change the fact that they differ on the right by that 1 element. So for abelian groups, this doesn't matter. For non-abelian groups, it is important that we keep track of the left side and the right side. Okay. So this defines a nice action. In fact, the action here of z on the Cayley graph here is exactly the action I told you at the beginning of class of the integer translations. Right? If you just add on an integer to 0, right, you're just going to send that to the corresponding thing, and you're just going to select that along. Right? What does the action of A do on this Cayley graph? Well, the action of A is just this counterclockwise rotation by 90 degrees, the way that I've had this thing drawn, right? A is just going to rotate this thing, 90 degrees. What does B do? B kind of swaps the inner and the outer shells. Okay? So now we have this nice group action on this nice metric space. Okay. And so one of the fundamental questions then of geometric group theory is how do geometric properties of the Cayley graph manifest algebraic. Now what about vice versa? Right? Is there any sort of geometric property of the Cayley graph that actually I can see just in terms of the algebraic structure? Right? Or if I see a certain thing geometrically in the Cayley graph, does that tell me something about the group? Right? And vice versa, right? Is there some sort of algebraic property of the group that I can necessarily find inside of the geometry? Right? How do these two things interact with each other? How does the geometry of this space really interact with the algebraic structure of the group? This is really sort of one of the motivational questions here in geometric group theory is to try to study the group, but not just looking at like a multiplication table for the group. Really thinking about the group and how it's acting on the space and really what's the geometry. I should tell you a warning, though, is that the Cayley graph really depends on this generating set. Okay, I've been keeping track of this generating set inside of the notation. And you might hope that, well, maybe there's only one Cayley graph for a group, right? That's not the case, right? So there are many Cayley graphs for a group, and they look kind of different. For instance, let's look at, here's a fun example. We looked at the integers already with the generating set 1. But there's lots of other sets I can use to generate the integers. For instance, I could take the number 2 and the number 3. Okay? And I could write down any integer as an integer combination of 2 and 3. Right? This is because these numbers have GCD. They're relatively prime, right? So I can write down 1 as an integer combination of 2 and 3. That 3 minus 2 is 1. And so anytime I can write down a number as 1, I can write it down as a bunch of 3's minus a bunch of 2's. Okay? And so, what does the Cayley graph look like in this case? Well, the vertices don't change, right? The vertices don't depend on the generating set, it only depends on the group. So let me go ahead and draw the vertices just like I did before. Over here. Okay, let's use some colors again. All right, so let's say 2 is blue. 3 is green. And the rule is then that I connect them up if they differ by 2 now with the green marker. And if they differ by 3, I connect them up with the red marker. And so I can draw these edges here on top. Okay, corresponding to the generator 2. And then on the bottom, right, I'll draw the ones of length 3. And so this is the Cayley graph for the integers using this generating set 2. You'll notice it looks different than the nice cute one we had before, right? Which was really just that combinatorial version of the real line. And you can really see this, and I didn't put the arrows on, right? But you can think everything is oriented to the right. And you can really see this relation, right? That 3 minus 2 equals 1 here inside of the graph, right? If I go along the red edge to the right, back along the green, right, you get, right? And you can see then, how to get from, you can sort of using that same idea, then to really see that this graph is going to be a connected one as long as you put down all of the edges. I forgot one. And so forth. And the group still at, oh, I forgot another one. I'm really bad today. Let's see, everything should have degree 4, right?
So you're only going to see connected graphs when you're looking at the Cayley graph?
Yeah, so this, let's see. This is something else that you can prove when you're bored tonight, is that as long as your set is actually a generating set, you'll get a connected graph. Yeah, so you can really use this expression of how you write down an element to build a path so that you can see that it's connected. It's an equivalent condition. I mean, you can define this graph for any set, but it's a generating set precisely when the graph is. Okay. The action is exactly the same. I mean, you have this sort of, you can translate this whole picture, 1 unit to the right. So the action is really the exact same on the object, although the object is different. However, it's not that different, right? I mean, imagine, I drew this picture here, and imagine you were like, sitting over in like Bell Engineering or something. You could look through the building or something, get X-ray vision. And I drew the other picture of the Cayley graph, right? They would look pretty similar, right? I mean, they're both sort of long and skinny, right? The farther back you step, I mean, the more that you really kind of forget the fact that, this thing has a little bit of width to it here, and it really just looks like, this really long, skinny object. And so, when we think about the geometry of the Cayley graph, we don't want to think about like the actual geometry, the actual metric space itself. We want to kind of loosen that notion up. We want to allow for the fact that like I should really think of this as being the same thing as the real line. Okay, I don't want to distinguish between those two things. From the point of view of geometric group theory, they really look like exactly the same. So let me go ahead and write down a definition that makes that precise. And the idea is that we just want to look at geometric properties that are okay up to this notion of equivalence. This is what's called a quasi-isometry. We can just write down a general definition. So let x dx and y dy be metric spaces. Secretly, we can think Cayley graphs, but it doesn't matter. So a function f from x to y is a quasi-isometry if, so two things need to hold, right? First off, well, it's an isometry sort of loosely, right? So I'm allowed to sort of stretch things. I'm even allowed to sort of break things. This is sort of one place in math where you're allowed to think about functions that are continuous, but not that much. So formally, what does this mean? It means if I look at the distance between 2 points, if I take the image of 2 points in y, right, and look at their distance, well, if this was an isometry, this should actually equal the distance between x and x prime and x, okay? Well, it's not quite, but maybe there's some sort of multiplicative fudge factor. Let me just call this, say, a. Right? So maybe the points, they can stretch a little bit. Maybe, in fact, they can even shrink a little bit. Oh, sorry, I guess 1 here should be, there exists some constant a, greater than 1, such that blah, blah. Right, so this is saying I'm sort of allowed to sort of stretch it a little bit, okay? This is really, maybe you've heard the words of a bi-Lipschitz now. So you're allowed to sort of stretch and shrink, but just in a sort of bounded amount. But now I'm also allowed to sort of tear things. So I can add on some sort of bounded additive error. Subtract out. Okay. So this says, I'm allowed to sort of bend it and stretch it, but not too much. And I can also sort of break it, but again, not too much. Right, there's sort of bounded controls on how much you're allowed to use. And then two, oh, sorry. I needed some constant up here. So if there exists an A, such that, so the constant for A, otherwise there's like 4 different constants, so let's just kind of keep one constant here. For all elements in Y, there exists an X in X, such that the distance in Y between little y and f of x is at most A. Okay? So the map isn't onto, right? If A was 0, the map would be onto, right? It's just saying everything is the image, but it's almost onto. Okay? Almost onto, and you're allowed to sort of stretch it. And this is enough then to see that with this notion, Cayley graphs are well defined. So here's yet another thing to prove when you're bored. Hopefully you're really bored today. You're going to prove all these things. So if I have finite sets, if S1 and S prime are finite, then the Cayley graph for S is quasi-isometric to the Cayley graph for S prime. Okay?
Those the generating sets?
Yeah, I guess there should be generating sets, yeah. Okay. And so when we look at these geometric properties of the Cayley graph, we can't just take sort of any geometric property. We really need them to be invariant under quasi-isometry. So that now that's not just a property of the Cayley graph with that generating set, it's in fact a property of the group. Because if one Cayley graph has that property, then the other one must also have that property. Okay? We happy? Okay, so in the little bit of time that we have left, let me go ahead and tell you about one such property and what it can actually tell you about a group. So the property is what's called ins. So ins of any group. So how is this defined? Well, let's call this E of G. Okay, so the definition here is I take the limit as n goes to infinity, and I want to look at the number of unbounded components. Of the Cayley graph with respect to a generating set, minus the ball about the identity element of radius n. Okay. So look at the Cayley graph, but then remove all of the portion of the Cayley graph that lives within distance n of the identity element. Okay. What do you have left? Count how many unbounded components. Take that limit as n goes to infinity, and this is what is known as the ends of. All right, so let's go ahead and look at our examples so that you can kind of get a feel for what this number is. And I guess I should say proposition. This one, I guess, maybe it's sort of increasingly becoming slightly harder, is that this is well defined. Right, in order to compute this, I have the generating set S over there, but the whole proposition is saying that, in fact, it doesn't depend on what generating set is. Okay. I mean, you can make this definition for any metric space, and if two metric spaces are quasi-isometric, they have the same number. Right, I should say, what type of object is this? I mean, this is, it's either, a non-negative integer, or it could possibly be infinity, right? If the number of unbounded components grows without being bounded above, then we just say that the number of ends. So let's look at some examples. Okay. We want to take a stab at how many ends the integers have. Yep, 2. Right, so if I draw the Cayley graph, and I'll just draw it, like the real line. What am I supposed to do? I'm supposed to remove out some chunk of, everything that lives within distance n of the identity element. If you throw out that chunk, there's 2 unbounded components left, right? Everything that's bigger than n and everything that's less than negative n. And there's always 2 unbounded components. Okay. Okay, let's look at another example. Okay, so the number of ends of the integers is 2, right? And I did this for, this is sort of the Cayley graph using degenerating set 1. But that other picture I drew had that same property, right? If I remove some chunk in the middle, there was really some piece corresponding to, very, negative numbers and another piece corresponding to very positive numbers. And those sort of pieces were connected, but they weren't connected unless you went through. Let's look at another example. How about the number of ends of this other Cayley graph we drew? Right, so remember the sort of the picture of the Cayley graph, right? This. Everyone wants to be so bold, I guess. Yep, 0. Right? Because, everything here is at most distance, 3 from the origin, right? So once I have distance 4, I've completely removed the entire thing, right? In fact, the number of ends of any finite group is 0. Oftentimes, geometric group theory, finite groups don't really have a huge role. Or I guess geometric group theory doesn't have much to say about finite groups, sort of the take away, or at least ends of the group. Finite groups do play a role sometimes in geometric group theory, but geometric group theory oftentimes sort of just completely blurs everything to do with finite groups. They're all sort of the same thing as the trivial group from this point of view. Okay. Let's look at a couple more examples. So this one I was looking at z mod 4 plus z mod 2. What if I just took z plus z? So you should think of this as like the sort of like the square lattice you see in R2, right? So if you use the sort of the standard basis of R2 as your generating set, then the Cayley graph exactly looks like this square lattice, right? This would be like the vector 0, 0. This would be the vector I guess 1, 0. 1, 0. This would be the vector 0, 1. And so on, right? So you're going to have all of the integer vectors, and then they're connected by sort of the obvious horizontal and vertical lines using this as your generator. Right? Just kind of like it was for R, right, where it was just a combinatorial version of, or sorry, as it was for Z, where you had a combinatorial version of the real line. This one we're just going to get this square lattice. Okay. Venture, how many ends? Infinity? Not quite. Less than infinity. Well, what happens if I remove, say, this one? How many do I have? If I just remove, say, the identity vertex. It's just 1, right? I could just always kind of, this path here that would have gone before, I can just kind of go up, over, and over. If I remove, say, these middle 4 squares, there's still 1, right? Because I can just go over here from the left. I can go up high enough, I can go over, and then I can go back down. And it's the same picture, right? No matter how big of a chunk I remove from the middle, I'm always going to just have 1 end, right? I can always avoid that chunk by going around. Right? If I remove this piece, there's still only one unbounded component. I can always just avoid it. In fact, yeah, I mean, if you want to, you can think not of, sort of this discrete object of this, integer lattice. If you just think about the plane R2 and removing a disk in R2, right? If you remove a disk in R2, it's still a connected object. That's exactly what this is. Okay, let's do one more. Okay, so this is a different group. Perhaps you haven't seen it unless you've taken an algebra class here so far. So we're not going to look at the direct sum or the direct product of Z and Z. We're going to look at the free product. Okay, so this is a free group of rank 2. So what is this group? Well, one way to think about this, you're just going to look at words in, say, the letters A and B. Okay, plus or minus. Right, so you're just going to, the group elements here are just, words in A and B, and also their inverses, so that it's actually a group. Or it's a reduced word, right? So you don't do anything silly like write A times A inverse. That's silly. And then the group operation is just concatenation. Just write one word and then the next. And if we start building the Cayley graph for this object, well, I start with the identity. And then, I'll have these elements corresponding to the word A, B, A inverse, and B inverse. And remember, there's this symmetry in the Cayley graph. So this is really the same picture I'll kind of see in all of the vertices. So at A, again over here on the right, it should have something of degree 4. So that would be the vertex, A squared. This would be the vertex AB. And this down here would be the vertex AB inverse. And whereas this group was an abelian group, this group is non-abelian. So one of the differences here is that AB and BA are in fact different elements. And I'll see this same picture, again, all of these things. This is going to be an infinite group, so, I can't draw the whole thing again. B inverse A, B inverse A inverse, A minus 2, A inverse B, A inverse B inverse. Again, right, it's a non-abelian group, so, those things are not the same, and those guys are also not the same. So the Cayley graph, what it looks like is this is going to be an infinite 4-valent tree. Okay, so it's a graph without any cycles. And every vertex has degree 4. So an idea here about the number of ends. This time it will be infinity. But if I remove the identity element, I get something with 4 components. If I remove things of distance 1, I'm going to get 12 components, right? Each one of those components before breaks up into 3 additional ones. When I do the next step, each one of those components, right, is going to now break up again. So now I'll have 36 ones on the next level. Again, multiply it by 3 the next time. 3 times 36 is 108. 108 components the next 3. So each time I remove a ball of radius n, I'm going to have, it's like 4 times 3 to the n minus 1 or something, number of components. So it'll be infinite in this case. Okay. Questions on that? Okay, so let me go ahead now and write down a theorem relating the ends of the group to the group structure. And in fact, what we'll see is that the examples we've looked at sort of illustrate everything that can possibly happen. So here's a theorem, which is due to Hopf from the 1940s. It says the following. So let G be a finitely generated group. Right, so it actually has a finite generating set. And you notice I didn't talk about the Cayley graph of a group like R, right? R doesn't have a finite generating set. And the group SL2R, the one we looked at before, that one also doesn't have a finite generating set. If you restrict yourself to integer entries, it does have a finite generating set. Anyway, we need this condition. Then the first statement here is that the number of ends of the group, well, it's one of these 4 examples that we've seen. So the 4 examples that we've seen are in fact the only things that can possibly happen. So either there's 0 ends, there's 1 end, there's 2 ends, or there's infinite ends. Right, so you're never going to come up with a group that has 3 ends, no matter how hard you try. The second one, this kind of tells a little bit about maybe the baby theorem from geometric group theory, right? The ends of the group is 0 if and only if the group is finite. This is pretty easy to convince yourself of. But this is kind of a prototypical theorem from geometric group theory, right? This is some statement about the geometry. And this is, well, I don't know, don't want to call this a statement about the algebra, right? But this is some statement about the group, right? And this connection here between the geometry on one side and the group structure on the other is sort of a prototypical theorem from geometric group theory, right? Trying to understand the geometry and seeing how that relates to it. Like I said, this one's pretty easy. The next one here is a little bit more technical to write, but maybe this is a better example. So this is an exact characterization of groups with 2 ends. Okay? So sort of the takeaway message here is that a group that has 2 ends really looks a lot like the integers. That's essentially the only group that has 2 ends. But we need to make that precise. So a group has 2 ends if and only if there exists a subgroup H of finite index so there's some sort of finite index subgroup, right? Remember the index is the number of cosets, right? So there's some finite index subgroup where H is isomorphic to the integers. Right, so maybe G looks like the integers direct product Z mod 2 or something. Okay? That doesn't change the group that much. It's just going to sort of, rather than having one line, you're just kind of stack 2 lines on top of each other. It still is going to look like it has 2 lines. But this is maybe a better sort of prototypical example of a geometric group theory statement, right? So here's some statement about the geometry, right? That the Cayley graph has exactly 2 ends. And here's some statement which is just about algebra, right? You're just saying that this group has this finite index subgroup, which is isomorphic to the integers. So really this connection here between the geometry of the space, we can sort of exactly say how it happens just in terms of the algebra. Okay? And let me just finish by just one more thing. So there's an Arkansas plays a key part in this story. So there's an undergraduate alum from Arkansas by the name of Stallings. He graduated in 1959. So if you go out on the senior walk, find his name, it's right by Mullins. And he gave a characterization. It's a little bit more complicated to state, but I can tell you later if you're interested. And he gave an algebraic characterization of what it means to say that the number of ends of a group is infinite. So there's also sort of a characterization of what it means to say that the Cayley graph has this kind of behavior, where you take bigger and bigger balls, you disconnect the Cayley graph into more and more pieces. There's an algebraic way of sort of detecting that, or vice versa. That process, has some sort of implications on the algebraic structure. Yeah, I should say this first statement too also isn't that hard as well too. If you're curious, you can swing by my office later on, and I can sort of draw a picture to convince you why this is true. Why you'll never find something with exactly 3 ends. But I believe I've already gone over like 5 minutes. So thanks for your time.